So yesterday we talked about completing the square, which converted a quadratic function that's in standard form into vertex form. And one of the things that's good about that is that it allows us to graph really easily. The other thing that's handy is that it tells us exactly the coordinates of the vertex. And the vertex is also a maximum point or a minimum point. And this is important to know when we're solving an application problem. Okay? Because a lot of applications deal with a maximization or a minimization, where we're trying to maximize something or trying to minimize something. Okay, so we're gonna go through a couple of examples of that, and here's the first one. A sporting goods store sells reusable sports water bottles for $8. At this price, their weekly sales are approximately 100 items. Research says that for every $2 increase in the price, the manager can expect the store to sell 5 fewer bottles. What selling price will give maximum revenue? Okay, so what we're trying to maximize here is the revenue from these water bottles. Okay, now when you're approaching a problem like this, you have to think carefully about what are the two variables that we're comparing here. Every function associates one variable with another. Okay, so what do you think one of them is going to be? Yeah. Okay, selling price. Yeah. What's another one? Yeah. Revenue. Okay, yeah, so something to do with price and revenue. We want to maximize revenue, so for sure that's going to be one of them. Now the price is currently at $8, and then we can increase it in increments of 2. Every time we increase it in increments of 2, the number of items that we sell decreases by 5. Okay, now how do you calculate revenue? Do you guys know what revenue is? How would you describe revenue? Yeah. Yeah, so revenue is the amount of money that you actually take in where you don't consider the costs. Right? So if you're selling, let's say you're selling ice cream. Or I don't know, let's say have any of you guys had a lemonade stand when you were little? Yeah, a couple of you? Okay, so you're selling lemonade on the corner, and you sell these cups of lemonade, and then you take in, I don't know, 50 cents or $1 or whatever from people who drive by, okay? The revenue is all the money that you take in from the people, not considering how much you had to pay for the lemonade and for the cups and all that. Okay, it's just the amount of money that you take in. If you consider the costs that went into you buying the lemonade, that's called profit. Okay, so yes, revenue. Oh, whoops. I gotta do that. Okay. Is number of items sold times the price of each item. Okay, so for example, what is the current revenue? If this store owner does nothing, if this sporting goods store does nothing, what would the current revenue be? Yes, $800, right? Or no, yeah, wait, 500 times 8? No, 100 times 8. Yes, 800. Thank you. It's Friday, right? $800, exactly. Okay. Now, the research shows that every time you increase the price by $2, this goes down. Okay. So if we make one of the variables price, we're going to have a problem because when this goes up, this goes down. So we can't make the other variable price. What we have to make the other variable is the number of times we increase the price by 2, because that affects both the price of each item and the number of items sold. Okay, so we're going to introduce a variable. Let the number of $2 price increases be X. Okay, now what we can do is we can actually come up with an expression for both the number of items sold using X and the price of each item using X. Okay, let's start with the price of each item. If I do one price increase, what would the price of each item be? $10, right? Because it's 8 plus 2. If I do 2 price increases, it would be $12 because it's 8 plus 2 times 2. If I do 3 price increases, what would it be? 14. It's 8 plus 3 times 2. So this piece is 8 plus, whoops, not times, plus 2x. It's 8 plus 2 times the number of times I increase the price. So if x is 10, if I do 10 price increases, that means I've increased the price by $20, because each increase is $2, and the total price would be $28. Okay? Now every time I do a price increase, the number of items sold goes down by 5. So if I did 1 price increase, how many items sold would I have? 95. What about if I did 2? 90. So every time I do a price increase, this guy, it starts at 100, but it goes down by the number of times I do that price increase. Okay? So this is our function. Okay? Now, if we expand this and put this into standard form, this is not in standard form right now. It's in factored form. Okay, so I'm going to expand it, which means I have to multiply these out and multiply these out. Right, so R of x equals 100 times 8 is 800, and then plus 200x, and then minus 40x, and then minus 10x squared. Okay, so when I simplify, my function is, and I'm going to also write out the terms in the function in decreasing powers of x. Okay, so I'm going to write the x squared term first, and then the x term, and then the constant. So negative 10x squared, and then 200x minus 40x is plus 160x, and then plus 800. Okay, now the question asked, what did the question ask? What selling price will give the maximum revenue? Well, to figure out the selling price, I need to know x, because the selling price is 8 plus 2x. Okay, I need to know x at the maximum point, because the maximum point is the maximum revenue. So if you imagine, this is, actually we should talk about this too. This is a parabola, and the a value is negative 10. So the a value is negative. What's the direction of opening? Down, yeah. So this is going to look like this. That means it has a maximum point. Okay? If r of x is on the y-axis and x is on the x-axis, the y-coordinate of the maximum point is our maximum revenue. And so that's why the coordinates of the vertex are very useful to us. Okay? So at this point, if we convert this into vertex form, we can solve this problem. So what we're going to do now is complete the square. Convert this into vertex form, which is what we looked at yesterday. Okay? So now, of course, you could solve this graphically. You could graph it and find the max point graphically. Okay? But I may ask you to do this specifically algebraically. And if I ask you to do it algebraically, that's what I would expect you to do. Okay? So when we are completing the square, what do I have to do first? Yep. Yeah, so if I look at these two terms and group them, yeah, I got to factor out the a value from those two terms, okay? So I'm going to take out the negative 10, and I'm left with x squared, and then what would go here? Minus 16x, yes, plus 800. And this has to be negative because negative 10 times negative 16 is positive 160. Okay? Okay, what next? What should I do next? Yeah. Yes, divide negative 16 by 2, which is negative 8. Square it. What's negative 8 squared? 64. So, and then I add and subtract that inside the bracket. Okay? All right. Now what? Yep. Yes, so I'm going to take this last term out. And to take it out, I actually have to distribute the negative 10 to the negative 64. So I have to go negative 10 times negative 64 plus 800. Okay? And now, I can write this as a perfect square trinomial, because that's what it is by design. What would the perfect square trinomial be? Yep. Yes, x minus 8 squared. And then this is negative 10 times negative 64 is 640 plus 800. So 640 plus 800 is 1,440. Okay, now what this tells me is that the vertex, which is also a max point, is at a specific coordinate. What's the x value of the vertex? Yeah, 8. Because the x value of the vertex is the p value. So this is 8. And what's the y value? 1,440, yeah. Okay, now what can we take from this? Well, if we go back here, okay, okay, 1,440 is the maximum revenue. Okay, 8 is X. Okay, now you don't want to answer 8 though, because you need to go back to your let statement and think about what does 8 or what does X actually represent? X is the number of $2 price increases. So if I have 8 $2 price increases, how much have I increased the price by? $16. So what's the new price going to be? Yeah, 24. Because it started at 8, and then I increased it by $16. Right? So it's 8 plus 2x, which is 8 plus 2 times 8, which is $24. Okay, so this is called a maximization problem. We are essentially creating a function that relates two variables together and algebraically figuring out what's the value of one variable that will maximize the other variable. Okay, questions with that one so far? All right, let's look at another one. Okay, so a farmer wishes to enclose a rectangular region bordering a river, and he wants to divide the region into 2 equal parts. What is the maximum area that can be enclosed with 600 feet of fencing? Okay, where do you think would be a good place to start with this one? What do you think would be a good thing to do? What's that? He wants to enclose a rectangular region bordering a river, and he wants to divide the region into 2 equal parts. What do you think we should do? Just with that sentence. Yeah. I would do something even before that. Probably something that maybe younger kids would think of. Draw it, yes. Right? We're looking at a maximum area of a rectangle, right? Let's draw it, okay? So what should go into my drawing? River, yeah, for sure. So here's the river. And he's gonna make a fence that borders the river. Okay, so maybe he's trying to like enclose animals that are really scared of water. I don't know, maybe it's cats. I think cats don't like water, right? Does anyone have any cats? Yeah, I think cats avoid water. So maybe he has cats and he's trying to enclose the cats and he knows the cats aren't gonna go in the water, okay? So he's making a rectangular, almost like a pen, that's bordering a river. Okay, and he wants to divide that into 2 equal parts. Okay. What's the maximum area that can be enclosed with 600 feet of fencing? Okay, so firstly, what's the formula for area? How do we find the area of a rectangle? Length times width. So maybe let's make those our two variables. Okay, this is our length because that's what we're trying to maximize. And this is our width. Okay, now there's a piece of information that we're given that we haven't used yet. What is that information? Yeah. Yes, 600 feet of fencing. Now, what do you think that's going to have to do with? Yeah, perimeter, exactly. Okay, now this isn't exactly a sort of typical perimeter, right? Because we're not going to put a fence up against the river. And then we only have one length, but 3 widths. Okay, so we kind of have to make up like our own perimeter expression here. But what we know, or equation, is that length plus 3 widths equals 600. Does that make sense? Okay, now we have a problem with our area. Area is what we want to maximize, right? So we actually want area to be a quadratic function because quadratic functions have a maximum point. But the problem with this function as it is it's got too many variables. Area is a variable, length is a variable, and width is a variable. So how could we use this to help us? Yeah. How would you do that? Could you use this relationship to maybe find an expression for L that uses W? Yeah. Yeah. L equals 600 minus 3W. Okay, now what could we do with this? What could we do with that? Yeah. Convert it to what? Well, this isn't a quadratic function yet. We've got a problem here, though. We want a quadratic function, but it's got too many variables. Now, we had another relationship between length and width. And what we did with that relationship was that we were able to express length in terms of width. How can we use that to help us with the fact that we have too many variables? What can we do with this? If length equals 600 minus 3 widths, yeah. Think about what you did last year, maybe when you were solving systems of linear equations. Yeah. Yeah. Sub that in. Do a substitution. If length equals 600 minus 3 width, we can use this expression, 600 minus 3 width, for length in the area equation. And then we only have 2 variables, area and width. Okay, so what we're going to get, maybe I actually should have, whoops, I'm going to do this. I'm going to, so that I have space to write, I'm going to do this. Okay, so we're going to get area equals 600 minus 3 width times width. This is good because now we only have 2 variables. Okay? So when you get these types of equations, and these ones come up quite a bit where you have an area and a perimeter situation going on. Okay? You want to write out a couple of relationships. One of them will be area, one of them will be perimeter. And then use one of the two to express one variable in terms of the other and do a substitution so that you can get a quadratic function that only uses 2 variables. Okay? Now we can expand. Right? So I'm going to get area equals 600W minus 3W squared. And this I can now convert into vertex form. Okay, so actually what I'll do first is maybe switch around the order of the terms. Okay, and now I have to, there's no constant here right now, so I can group these two together. I'm going to factor out my A value. Okay. When I factor out a negative 3 from 600, positive 600, what do I get left? Negative 200, yeah. Okay, so negative 3 W squared minus 200W. Okay, now I have to take half of that, which is negative 100, and square it. Negative 100 squared is 10,000. So plus 10,000 minus 10,000. Oh, I forgot a 0. That doesn't look very good. Okay. I'm squishing things together here. Okay, and then I can remove the last term from the bracket. I'm not going to have room. So minus 3 times negative 10,000. Okay, so my function in vertex form is A equals negative 3 times this becomes W minus 100 squared, and then plus 30,000. Okay. This is not my final answer, though. We have to go back and look what the question was asking. Okay, what were we asked for here? We were asked for what is the maximum area that can be enclosed. So what's the maximum area? If you were to put this on a graph, area and width, which variable would go on each axis? Would area go on the y-axis or the x-axis? Yep, the y-axis, right. Okay, where's the vertex? What are the coordinates of the vertex? Yeah. Yep, 100 and? Right. $130,000. Okay, so you need to be able to kind of visualize that and know what these two values mean in the vertex form so that you can actually answer questions about the situation. Because I could have asked you anything. I could have said, well, what length would maximize the area? What width would maximize the area? What is the maximum area, right? Maximum area is 30,000, right? It's the y coordinate of the max point. The width is 100, okay? What would the length be? Yeah. How would you figure out the length? Yeah. You could, but actually, remember when we subbed in originally, we had length equals 600 minus 3 width? You can go back to that because then you have length isolated already, right? And just plug 100 in for width, right? So I'm running out of space here, but I'll find a spot to put it here. So max area equals 30,000 feet squared. Width equals 100 feet. And length equals 600 minus 3 times 100, which is 300 feet. Okay, so I could ask for any one of those three. Now, you could certainly verify your answer using technology, right? You could graph the original function, or you could graph it before you complete the square and find the coordinates of the vertex to make sure that you're doing it correctly. But if I asked you to show an algebraic solution, then this is what I would expect. Okay, now this last one, an explosive is launched at a snow slope. The equation for the explosive's height in meters at time t seconds is h of t equals negative 4.9 t squared plus 19.6 t plus 58.8. What is the maximum height of the explosive? Okay, in this situation, you're given the function. So you don't have to come up with that yourself. Okay? What I want you guys to do is to work on this one yourself. And then if we need to, we'll go through it as a group. Okay?